Section 1. Hey guys. Tonight we slip into the dusty corners of a quiet study where light from a single lamp glows. Across piles of papers, chalk dust drifts lazily through the air, and the scratch of a fountain pen echoes like a secret code. It's Einstein's studite place where old wood creaks under stacks of journals, where coffee stains mark the edges of cosmic revelations, and where time itself might feel just a little bit slower, as though lingering out of respect. You're about to discover how gravity doesn't just pull apples from trees, it stretches, bends, and sometimes traps time itself. And fair warning, you probably won't survive this with your mind completely intact, because pondering how gravity warps not just space, but time is one of those delightful journeys that might leave you lying awake at 3 a.m. wondering if your watch is lying to you. So, before you get comfortable, take a moment to like the video and subscribe a bit, only if you genuinely enjoy what I do here. And hey, let me know in the comments where you're listening from and what time it is right now. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. So there you are, floating right behind Einstein as he pushes papers around his chaotic desk. Ink stains smudge the cuffs of his shirt. The air smells of chalk, old books, and maybe a whiff of pipe smoke. His hair is a wild storm cloud, caught somewhere between genius and static electricity. And in that cluttered room, he's scribbling out equations that will reveal a truth so wild it makes the universe seem like a magician hiding cards up its sleeve. Because in 1915, Einstein told the world that gravity wasn't merely a force pulling objects downward. It was geometry, space itself and time, too warped in the presence of mass. Mainstream fact for you: before Einstein, people imagined gravity as an invisible force that tugged on objects. But general relativity showed that mass and energy bend the fabric of spacetime, creating curves that objects follow naturally. So when an apple falls, it's not being pulled so much as rolling along a slope in curved spacetime. And your quirky Einstein tidbit: despite changing how we see gravity, Einstein himself was famously absent-minded. He once forgot where he lived and had to ask a policeman to help him get home. Physicists still argue whether that absent-mindedness was the price of genius or just a convenient excuse for avoiding small talk. Either way, I'd bet that violin he kept under his desk knew the way home. Hovering behind him, you peer over his shoulder and see the equations twisting into elegant curves. The symbols dance and spin as though performing a cosmic waltz, and you realize that those curves don't just describe how space stretches, they dictate how time itself ticks forward. Because here's the mind-bending part: gravity changes time's pace. In strong gravity, clocks run slower near massive objects. Seconds stretch longer than they do far from those objects. It's as if gravity places a gentle hand on time's shoulder and says, "Slow down." Physicists still argue whether this warping of time could one day be manipulated or harnessed in technology. Could we create areas of stretched time to slow aging or speed up processes? Or will time forever remain beyond our engineering reach, just an elegant byproduct of cosmic mass? The debate pulses on, from research papers to hushed conversations at physics conferences, where coffee cups shake from both caffeine and existential dread. Einstein's violin leans in the corner, a silent witness to this drama. Maybe its strings vibrated in sympathy while he puzzled over how time bends near stars, how the ticking of clocks changes depending on where and when you stand in the universe. You imagine him pausing mid-note, eyes unfocused, whispering, "Time is not absolute." And right then, the quiet beauty hits you. The universe isn't merely space littered with planets and stars. It's a dynamic fabric where gravity weaves invisible valleys and ridges, not only in the roads objects travel but in how moments unfold. Your heartbeat quickens as you picture gravity bending space around massive objects, creating invisible curves that planets roll along. Yet you also sense how, in these curves, time itself can stretch like warm caramel. Minutes become longer, seconds grow shy and hesitant, and the past and future might lean closer than you ever dared to think. You hover above Einstein's desk, awash in lamplight, feeling both tiny and impossibly connected to everything. The coffee stains, the chalk dust, the violin's silent stringshire, all reminders that the same gravity shaping galaxies. also gently shapes the seconds ticking in your life. And that's where our journey begins tonight, in the cluttered calm of Einstein's study, where gravity's secrets pour from ink-stained page sand, where you're about to discover how those secrets warp not just space, but time itself. Remember that violin leaning under his desk? We're going to come back to it. Trust meets part of the music woven into the fabric of spacetime. Section 2. You're still hovering above Einstein's desk, the glow of the lamp warming your imaginary cheeks, when suddenly the room seems to dissolve away. The walls vanish, the stacks of papers fade, and you find yourself drifting through space itself, a place where curves are invisible, but as real as the beating of your own heart. Because tonight, you're going to explore how massive objects bend the unseen paths around them, reshaping not just the routes things travel but how time itself flows. Imagine floating through a silent, star-dappled void. You see a massive sphere of glowing gaseous star like our sun. Light streams outward in brilliant rays. But as those beams pass close to the star, you notice they don't travel in perfect straight lines. Instead, they bend ever so slightly inward, tracing gentle arcs through the cosmic darkness. Mainstream fact, this bending of light is called gravitational lensing, and it's one of the earliest and clearest proofs of Einstein's general relativity. During the solar eclipse of 1919, astronomers measured how starlight curved around the sun's mass. The world was astonished. Headlines screamed that Newton had been dethroned, and Einstein became a global celebrity practically overnight. Quirky Einstein tidbit: despite his fame, Einstein claimed he found all the attention deeply exhausting. He once said, "I never realized that fame would bring so many invitations to dinner." Physicists still argue whether he genuinely disliked the spotlight, or whether he secretly enjoyed the occasional free meal. One can imagine him sipping soup at a fancy dinner, silently plotting how to escape back to his violin. Floating closer to the star, you see the space around it ripple and curve as though it's wrapped in a transparent, flexible sheet. But it's not just space bending, it's time too. Near the star, clocks tick ever so slightly slower than they do far away. Physicists still argue whether this curvature of spacetime could one day be visualized, or measured directly on small scales, using advanced quantum sensors or new kinds of technology. Could we see space bending in real time, or will it always remain a mathematical ghost, only glimpsed through how it redirects light and shifts time's rhythm? You float beyond the star, watching light paths spiral gently around it. The scene feels almost balletic, as if photons themselves are performing a dance choreographed by gravity. And here's the twist: this graceful curve isn't just a curiosity, it shapes your entire existence. Because gravity isn't a force pulling objects along straight lines, it's the bending of spacetime, dictating the natural paths everything follows. Planets orbit stars not because they're yanked by an invisible rope, but because space itself curves around the star, creating a path that feels inevitable. Picture a marble rolling along a trampoline. If you place a heavy ball in the middle, the marble spirals inward, tracing curves that have nothing to do with strings or force and everything to do with geometry. That's your life in spacetime. You're rolling along curved surfaces, even if you don't feel the tilt beneath your feet. Einstein's violin flashes in your memory. Think of gravity's curves like the graceful bending of a violin string under the pressure of a bow. The vibrations change depending on how tightly the string is wound. Just as spacetime's curvature deepens near greater masses, the music, like gravity, shapes the flow of time around it. You imagine astronauts floating aboard the International Space Station, 400 kilometers above Earth. Up there, gravity is weaker than on the surface. Time ticks ever so slightly faster for them than for people on the ground. The difference might be only milliseconds, but it's real. The astronauts are literally living a sliver ahead in the future, compared to you scrolling your phone on Earth. Physicists still argue whether these time shifts could ever become significant, enough to matter in human experience. Could living at higher altitudes genuinely extend your lifespan by measurable amounts? Or will these differences forever remain fascinating trivia, smaller than the blink of an eye? The notion makes you grin, because you're now picturing billionaires building skyscrapers purely to gain a few extra microseconds of life. Live long, guarantee the penthouse might be the hottest new real estate slogan. Your gaze returns to the star's glow, You realize every massive object, stars, planets, black hole, excretes a region of curved spacetime around it, dictating the flow of time like a maestro conducting a symphony. Even your own body warps spacetime, though only by a ridiculously tiny amount. Sereno personal gravitational lensing selfies for your social media yet. Einstein once said he wanted to know God's thoughts, the rest are details. And as you float through these curves, you realize he was chasing how the universe weaves space and time into a seamless geometry that not only shapes cosmic pathways, but also writes the tempo of time itself. So tonight, as you look up at the stars, remember their beauty isn't just points of light in darkness. It's evidence that space bends, time stretches, and gravity is the universe's invisible choreographer, guiding everything from starlight to your next second on Earth through elegant, unseen curves. And hey, next time you feel the urge to blame traffic for making you late, just tell people, sorry. Guys, time runs slower down here in the gravitational well. See how that goes. Section 3. You're still floating among starlight and invisible curves when gravity tugs you gently downward, pulling you back toward familiar terrain. Your feet touch rocky ground, the air crisp and cool, and suddenly, you find yourself standing on the side of a mountain, your breath curling into clouds under a sky so clear it seems to stretch forever. Because tonight, you're going to climb higher and feel how gravity's soft grip on time changes the tempo of your very seconds. You look down at a glittering valley below. A river glints like a ribbon of glass. Pine trees sway in silent breezes. Everything seems normal except it's not. Up here, time is flowing just a tiny bit faster than it does down there in the valley. Mainstream fact, general relativity tells us that gravity slows time. The closer you are to a massive object like Earth, the slower your clock runs compared to someone further away. This isn't science fiction, it's measurable reality. In 2010, scientists used atomic clocks to prove that a height difference of just 33 centimeters makes time run faster by tiny fractions of a second. Quirky Einstein tidbit. Einstein once explained relativity in a delightfully cheeky way. He said, "When you sit with a nice girl for 2 hours, it seems like 2 minutes. When you sit on a hot stove for 2 minutes, it seems like 2 hours." Physicists still argue whether that analogy helps people understand time dilation, or whether it just gives folks an excuse to flirt or complain about stoves. Either way, you can't say the man didn't try to keep it relatable. Standing on the mountain, you pull a slim wristwatch from your pocket, a vintage piece, maybe something Einstein himself would have liked. You glance at the ticking second hand, then imagine an identical clock left back in the valley. Up here, your seconds are ever so slightly shorter. Not enough to notice in your daily life, but undeniably real. Physicists still argue whether these differences in time could ever add up to something meaningful in human lifespans. Would living your whole life on a mountaintop make you meaningfully younger than your identical twin, who stayed at sea level? Or is the gain so minuscule that you just end up with wine-chapped skin and a bigger coffee bill from the mountain cafe? And here's a fun thought. GPS satellites have to account for this effect constantly. Orbiting high above Earth, they experience weaker gravity and thus time moves faster for them. Without precise corrections, your GPS app could steer you kilometers off course. Imagine telling your phone to find the nearest pizza place, only to end up in a cornfield 3 towns over. Einstein's violin drifts into your mind again. You imagine him standing on this very mountain, bow in hand, drawing a slow, rich note across the strings. Maybe he'd listen for subtle shifts in the echo, pondering how sound travels the same way light does across curves, over distances, stretched and compressed by gravity's quiet hand. Your eyes trace the rocky ridgeline, and you feel how the mountain itself warps the spacetime around it, though ever so slightly. Even a mountain adds its tiny ripple to the cosmic fabric, gently slowing time at its base more than at its peak. It's humbling to think that the ground under your feet subtly shapes how quickly your heart beats, how fast your neurons fire, how long your life seems to last. Physicists still argue whether these time differences might someday influence biological processes in detectable ways. Could aging be subtly affected by the speed of time's flow in different gravitational fields? Or does the body simply roll along, oblivious to relativity? As long as gravity doesn't flatten you like a pancake, you chuckle because you realize the classic quest for youth could take a weirdly practical turn. Forget anti-aging creams, perhaps the true elixir of longevity is simply moving uphill. Though, of course, it might only grant you an extra nanosecond or two. Still, every nanosecond counts when you're trying to binge your favorite show. Before spoilers hit the internet, as you look toward the valley again, you understand that time isn't uniform. It's sculpted by gravity, stretched and compressed by the mass beneath your feet. Clocks, humans, and even starlight obey this rule. Every tick of your watch is a gentle negotiation between you and Earth's gravitational embrace. Einstein once said he felt deeply religious, in the sense of standing humbled before the mysteries of the universe. Standing on this mountain, it's easy to see why. The silent peaks, the stars blazing overhead, the knowledge that even here, time runs a little differently, echoing whispers of a universe both intimate and vast. So tonight, as you lie in bed or drift off on your couch, remember, your seconds aren't the same as those ticking for someone at sea level. Time is elastic, bending and stretching across mountains and valleys. And next time someone brags about living at high altitude, just smile and say, cool. Enjoy your few extra nanoseconds of life. Section 4. You're still standing there on the mountain peak, cool wind tugging at your hair, when gravity gives you a gentle nudge. And suddenly, it's like you're leaning forward, teetering on the edge of motion, ready to tumble. Because tonight, you're going to feel how falling isn't merely moving through space but slipping along a shortcut, through curved time itself. You take a step forward, and then another, and suddenly whoosh, you're falling down the mountain slope. Rocks blur past, air roars in your ears. It's terrifying and thrilling all at once. But here's the cosmic twist. According to Einstein's insights, when you fall, you're not being pulled by gravity the way Newton imagined. Instead, you're simply following the natural curve of space-time, a path that requires no force at all. Mainstream fact, in Einstein's general relativity, objects in free fall are moving along paths called geodesics. These are the straightest possible lines in curved spacetime. To you, the fall feels dramatic, even violent, but in a purely local sense, you're weightless, floating along the natural shape of gravity's curves. Quirky Einstein tidbit. Einstein once described riding in a falling elevator as one of his happiest thoughts. He realized that during free fall, you'd feel weightless because you and the elevator would be accelerating equally. Physicists still argue whether his so-called happiest thought was the true spark that birthed general relativity, just one delightful moment in his lifelong habit of daydreaming. Either way, it's comforting to know that while the rest of us panic in falling elevators, Einstein was quietly inventing modern physics. As you tumble down the slope, time seems to stretch and compress in strange ways. Your mind slows to capture each leaf whipping past your face, even as your body plummets faster. This isn't just adrenaline, it's a glimpse into how motion and gravity warp your sense of time. Physicists still argue whether extreme free-fall paths, like those near black holes, could be used to explore the very structure of spacetime. Could a perfectly calculated fall let us skim the event horizon and return, gathering data without being spaghettified? Or is that just sci-fi bravado with a hefty side of certain doom? You recall Einstein's violin under his desk and imagine the bow moving along a gently curved path. In the same way, your fall traces the curvature of spacetime. Gravity isn't forcing you downward, it's just defining the easiest route for your body to travel. The violin string bends under tension, your path bends under gravity. Different instruments, same universal music. When astronauts orbit Earth, they're actually in perpetual free fall. They fall toward the planet. But because they're moving sideways so fast, they keep missing it. Their trajectory forms a graceful curve around the globe, a perfect balance between gravity's pull and forward motion. Up there, astronauts feel weightless not because there's no gravity, but because they're following spacetime's natural curves. Just like you plummeting off the mountain, physicists still argue whether true weightlessness can ever be experienced indefinitely, or whether even the softest cosmic curves eventually tug us back toward some gravitational center. It's a debate that fuels not only scientific papers, but sci-fi plots about eternal floating cities and carefree cosmic surfing. Your tumble slows, You land gently on a patch of mossy earth, miraculously unharmed because height's bedtime story physics. And we can take a few liberties for comfort's sake, brushing off imaginary dirt. You ponder how everyday experiences like falling are connected to cosmic truths. Your morning stumble on the sidewalk, your roller coaster scream, even the graceful swoop of a hawk diving for prey all are expressions of the same curved paths in spacetime. Einstein understood that gravity isn't an invisible hand yanking you down, it's geometry itself, sculpting the landscape of reality. Falling is simply moving along the contours of that geometry. You're gliding down the slopes the universe has carved into the shape of time. Think of light passing close to a massive object, bending along curves carved into spacetime. It's the same principle. The photon falls through curved space, tracing the shortest route. Everything from apples to starlight follows these invisible highways. Einstein's happiest thought echoes in your mind. Free fall erases gravity's pull, revealing the smooth pathways beneath. And you realize that falling isn't chaos, it's cosmic elegance, hidden in what feels like panic. So tonight, as you lie there drifting toward sleep, remember, gravity isn't simply pulling you down. It's showing you the shortest path through space and time. Your every step, your every stumble, follows the gentle curves sculpted by the massive earth beneath your feet. And hey, if you ever do trip and fall tomorrow, just tell people you are following a geodesic and curved spacetime. It won't make you less clumsy, but it'll definitely make you sound smarter. Section 5. You're still dusting off imaginary moss from your cosmic tumble when the world seems to ripple and darken around you. The stars pull back as though wary of what comes next. Because tonight, you're drifting toward one of the most extreme places in the universe, a place where gravity warps time almost to a standstill. Welcome to the edge of a black hole. At first, it's eerily beautiful. You float near the black hole's event horizontal invisible boundary, beyond which not even light can escape. Around you, space swirls like water spiraling down a drain. Starlight bends into brilliant arcs. The black hole itself looks like a perfect circle of darkness, framed by glowing matter whipping around it at near light speed. Mainstream fact: a black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. The result is a singularity, a point of infinite density surrounded by an event horizon. Near this boundary, gravity becomes so intense that time stretches almost infinitely. To an outside observer, anything falling in appears to freeze, trapped in slow motion. Quirky Einstein tidbit: despite the math suggesting black holes, Einstein himself doubted they could truly exist in nature. He believed the universe would find a way to prevent such absurdities. Physicists still argue whether his skepticism reflected deep intuition or simply a refusal to accept how bizarre his own equations could be. Either way, it's pretty funny imagining Einstein shaking his head at the universe, wagging a finger, and saying, "No, that's too weird, even for me." As you hover closer to the event horizon, you feel time begin to stretch. Your imaginary watch ticks slower and slower. From the outside, it would look like you were pausing, suspended on the brink of vanishing forever. Yet for you, time flows normally, your thoughts, your breath, your heartbeat all proceeding at their usual pace. Physicists still argue whether information falling into a black hole is truly lost forever. This puzzled black hole information paradoxes spark debates and mountains of papers. Does the information somehow cling to the event horizon, etched into quantum ripples like cosmic graffiti, or does it vanish into oblivion, leaving an unsettling gap in physics ledger? The stakes are enormous because if information can truly disappear, it challenges some of the most fundamental principles of quantum mechanics. Floating at the edge, you recall Einstein's violin leaning under his desk. You picture him playing a trembling note, one that fades and slows as it's drawn toward the black hole's gravity. The same way that light, climbing away from a black hole, stretches into longer wavelengths, turning from visible light to infrared, then to radio waves, until finally it's too faint to detect at all. Near the event horizon, even photons struggle. Light emitted from your wristwatch face loses energy, growing redder and fainter, until the universe seems to sigh and give up on seeing you ever again. Astronomers have glimpsed black holes indirectly for decades, but it wasn't until 2019 that humanity captured the first real image of a black hole's shadow. In the galaxy M87, a glowing orange donut surrounding a pit of darkness. Proof that gravity's sculpting power is both terrifying and magnificent. Physicists still argue whether black holes might connect to other parts of the universe through wormholes. Could they be secret doorways, not final destinations? Or does anything daring enough to slip through simply hit a cosmic brick wall? The equations sometimes suggest possibilities the universe doesn't always cooperate. With our favorite sci-fi plots, you float closer, the swirl of infalling matter growing hotter and brighter, emitting X-rays and gamma rays as atoms are shredded and accelerated. This is where black holes become silent sculptors of cosmic drama. They shape galaxies, regulate star formation, and power jets of radiation that blaze across millions of light years. It's humbling to think that black holes, born from stellar death, can influence entire galaxies, steering cosmic evolution from their hidden thrones. Their gravity not only bends space, it stretches time into slow-motion poetry, sculpting moments into endless delays. You imagine a spaceship daring to hover just above the event horizon. Inside, astronauts age slowly, while centuries pass for observers far away. In a strange way, black holes could be the ultimate time machine, one-way tickets only, and probably not covered by your travel insurance. Einstein's equations hint that near the singularity, the very laws of physics break down. Space and time lose their meaning, collapsing into a realm where no human intuition can follow. The idea that time itself might cease to exist as we know it enough to send a chill down your cosmic spine. So tonight, as you nestle under your blanket or sprawl on your couch, remember, gravity's power doesn't stop at pulling objects closer. It sculpts time, stretches seconds, and guards secrets at the thresholds of black holes. And if anyone ever calls you dramatic for running late, just remind them that time itself runs slower near strong gravity. Blame your inner black hole. Section 6. You're drifting gently away from the edge of the black hole, your mind still buzzing with stretched seconds and fading starlight. And suddenly, you feel the warmth of a distant sun against your cosmic skin, a reminder that gravity's strange grip on time isn't confined only to monstrous black holes. Because tonight, you're going to watch a star say goodbye in slow motion, and see how gravity can turn even a shining giant into a master illusionist, dragging time into a languid crawl. Imagine a massive star, swollen and radiant, burning through its nuclear fuel in spectacular fashion. At its surface, photons fight to escape the star's gravity. Each particle of light is like a tiny climber struggling uphill against a steep gravitational slope. Mainstream fact: light escaping from a massive object loses energy and becomes redshifted. It shifts toward longer wavelengths, like the lowering of a violin's pitch as the bow moves slower across the strings. The phenomenon is called gravitational redshift, and it's a direct consequence of how gravity warps both space and time. Quirky Einstein tidbit: Einstein didn't initially accept the idea of gravitational redshift without skepticism. It took several years and some persistent colleagues before he fully embraced the notion that gravity could drain energy from light. Physicists still argue whether Einstein's occasional stubbornness made him a more cautious scientist, or merely delayed the inevitable march of discovery. Either way, it's somehow comforting to know even geniuses need a little convincing sometimes. Hovering near the star, you watch the photons rise from its blazing surface. They emerge full of energy, bright, blue-white, searing hot. But as they climb through the star's gravitational field, they lose a fraction of their vigor, stretching into longer, redder wavelengths. To an outside observer, the star appears cooler, dimmer, softer in color. Physicists still argue whether gravitational redshift could help us peek deeper into stellar interiors. Could we read the precise frequencies of escaping light like a secret code, unlocking details about a star's structure, temperature, or even undiscovered forces? Or is this cosmic whispering simply too faint to ever reveal more than broad strokes? Einstein's violin returns to your mind. You picture him playing a note that starts sharp and high but gradually fades into a lower, deeper hum. Gravitational redshift is nature's version of the same musical trick. Gravity doesn't merely bend space, it changes the very music of the universe. transforming the colors and frequencies of light. As the star begins to collapse in its final stages of life, time itself slows dramatically near its surface. From afar, you'd see the star's glow fading not simply because it's cooling, but because gravity stretches each second into a longer moment. Events on the star's surface appear frozen, like a cosmic performance stuck on the longest crescendo ever played. You hover there, sensing the paradox. For the star itself, time continues as normal. Nuclear reactions proceed, atoms fuse, and matter rushes toward its final destiny. But for you, the observer floating safely in space, the star's dying moments stretch into near eternity. Physicists still argue whether this time-stretching effect might offer unique clues about supernovae or other explosive stellar deaths. Could subtle timing differences in light signals reveal secrets about gravitational waves, exotic particles, or dark energy? Or will gravity's hush keep those final moments forever private? Your gaze drifts from the star's fiery surface to the space around it, realizing how even light nature's speed champion cannot escape gravity's hold without losing something along the way. You think of GPS satellites again. Even their signals undergo tiny gravitational redshifts as they climb from Earth's surface. Our everyday navigation depends on adjusting for these shifts, so you don't accidentally drive into a lake instead of your favorite cafe. It's the mundane meeting the cosmic, a quiet reminder that gravity warps time, even in our daily routines. Floating there, you wonder how Einstein must have felt, realizing that gravity didn't merely curve space, but stole energy from light itself. That even color could shift under the weight of mass. It's the universe revealing its tricks in subtle hues, a cosmic magician playing with the wavelengths of reality. Einstein's violin echoes softly in your imagination, its strings vibrating in a slow, mournful melody. You realize that gravitational redshift isn't just a physics curiosity, it's a gentle message that the universe's beauty comes from how forces like gravity reshape everything, even the way we see starlight. So tonight, as you lie in the darkness, remember, every star you see has light escaping a gravitational climb. Those twinkles are tiny triumphs, each photon winning its uphill battle to reach your eyes, its colors softened by the cosmic weight of mass and time. And if someone tells you the stars look redder than usual, just smile and say, ah. Gravitational redshift, nature's own cosmic Instagram filter. Section 7. You're floating away from the glow of that slowly fading star, the crimson shimmer of redshift still dancing in your mind, when the universe gently nudges you back toward Earth. And suddenly, you're surrounded by a dizzying network of invisible beams, bouncing between sleek satellites, and the smartphones buzzing in countless pockets below. Because tonight, you're going to glimpse how even the gadgets you use every day depend on Einstein's realization that gravity warps time, twisting each second ever so slightly, and why your pizza arrives on time because of it. Imagine orbiting Earth in a shiny satellite, high above swirling clouds and glowing city lights. Down below, humans bustle through streets, check their phones, and argue about the best route to beat traffic. Mainstream fact: Jeep's global positioning system relies on satellites that carry atomic clocks, ticking with incredible precision. But here's the kicker: because those satellites are farther from Earth's mass, time runs a bit faster for them than for clocks on the ground. If we didn't correct for this time dilation, GPS locations would drift by kilometers each day. Your phone might think you're in another city entirely or floating somewhere in the ocean. Quirky Einstein tidbit: Einstein's genius sometimes bordered on the absent-minded. Once, he boarded a train without his ticket. When the conductor demanded it, Einstein searched every pocket in a panic. The conductor said, "Don't worry, doctor." "Einstein, we all know who you are." To which Einstein replied, "Yes, but I need to know where I'm going." Physicists still argue whether he genuinely forgot or if it was simply another of his dry jokes. Either way, it's proof that even the man who unraveled time could occasionally get lost in it. Floating alongside the satellites, you watch laser-like radio signals zipping back and forth between Earth and space. Every tiny difference in time, every nanosecond of clock drift translates into real distance errors. If satellites ignored time dilation, your GPS could steer you into a pond instead of a coffee shop. Physicists still argue whether future technologies might push these precision demands even further. Could quantum sensors someday reveal even tinier ripples in spacetime? Might we need to correct for time shifts so small they border on quantum uncertainty? Or will the differences always remain minor tweaks hidden behind user-friendly apps? Einstein's violin comes back into your mind. Imagine the delicate vibration of a single note, precise and unwavering. That's how the atomic clocks aboard GPS satellites behave, counting oscillations of cesium atoms with perfect rhythm. Except, of course, those rhythms warp in gravity's grasp. The satellite's clocks tick about 45 microseconds faster each day due to weaker gravity. But they also tick a tiny bit slower because they're moving quickly round Earth. It's an elegant cosmic balancing act, and without Einstein's equations, modern life would be hopelessly confused. Hovering in orbit, you feel a strange sense of power. You're seeing how spacetime's curves affect not just black holes or massive stars, but your daily existence. Whether you're hailing a rideshare, finding the nearest ramen spot, or navigating a plane across continents, you're leaning on Einstein's understanding that time bends in the presence of mass. Physicists still argue whether these time corrections could someday reveal entirely new physics. Might tiny anomalies in satellite data hint at hidden dimensions or dark matter's elusive presence? Or is GPS destined to remain merely a stunning practical triumph of Einstein's ideas? It's a question that fuels scientific paper sand, probably keeps a few physicists awake at night, staring at ceiling tiles while their cats judge them from the foot of the bed. Your gaze returns to Earth, and you realize how cosmic truths nestle quietly into the mundane. Time dilation sounds esoteric, but it's part of everyday life, woven into the soft hum of your smartphone and the reassuring voice telling you, in 500 meters, turn left. Einstein's violin seems to play softly as you imagine satellite signals shimmering, like strings vibrating across space. Each tick of the atomic clocks is a note in a cosmic orchestra, perfectly timed to keep you from getting lost even if Einstein himself might have. So tonight, as you glance at your phone's glowing screen, remember, behind your GPS pin, behind your morning commute, there's a dance of time and gravity unfolding silently above you. And next time you miss a turn because your GPS glitched, just sigh and say, ah. The relentless chaos of curved spacetime. It won't help your driving record, but it might make you sound impressively philosophical. Section 8. You're drifting back down from the GPS satellites, wrapped in a silent rain of signals and data pulses, when the universe gives you a softer, more intimate nudge. It's as though the cosmic stage wants to remind you that gravity's touch on time isn't only written into satellites and starlight, it's woven into human life itself. Because tonight, you're going to reflect on how motion and gravity subtly stretch our lifespans even if only by fractions, and how your very own seconds are shaped by cosmic curves. Picture yourself on an airplane, rocketing eastward at 900 kilometers per hour, sipping a paper cup of tomato juice and quietly pondering the meaning of life, as one does at cruising altitude. Unbeknownst to you, time is ticking a little slower for you than for someone standing still on the ground. Mainstream fact, special relativity tells us that motion slows timey phenomenon, known as time dilation. The faster you move, the slower your clock ticks relative to someone at rest. The effect is minuscule at airplane speeds, but becomes significant at near-light velocities. And general relativity adds another twist. The stronger the gravity you're in, the slower your clock runs. Quirky Einstein tidbit: despite pondering time's mysteries, Einstein was known to lose track of it entirely in his daily life. He'd sometimes forget to eat meals, once remarking that time only mattered when you look at the clock. Physicists still argue whether his absent-mindedness was charming genius, or simply the byproduct of a brain overloaded with cosmic secrets. Either way, it's proof that even the master of time sometimes let it slip right past him. Floating above Earth, you imagine de Twinson stays on the planet. The other boards a spaceship and flies at near-light speed for a few years before returning. The traveling twin is younger upon reunion. It's the famous twin paradox, where time's pace itself bends under motion's influence. Physicists still argue whether humans might ever build ships fast enough for time dilation to matter in practical terms. Could future explorers one day journey to distant stars and come back to find Earth centuries older? Or will relativistic travel remain a dreamy footnote in physics lectures and sci-fi novels? Back on your imaginary flight, your tomato juice wobbles in its plastic cup as turbulence rattles the cabin. You grin, realizing that while you're losing billions of a second due to your speed, you're also gaining a tiny fraction of time because you're farther from Earth's gravity than people on the ground. It's a cosmic balancing act happening quietly above the cloud tops. Einstein's violin flickers into your mind. You picture him bowing a single note, stretching it longer and longer, slowing its tempo until it feels suspended in midair. That's time dilation, stretching seconds, changing rhythm, turning time into a flexible melody. Physicists still argue whether these tiny relativistic effects could subtly influence biological processes. Could time dilation affect the rate of cellular aging, DNA replication, or even brain activity? Or are living systems so robust that they glide through these time shifts without noticing a thing? The debate tiptoes the line between physics and biology, a reminder that the universe loves to keep its secrets interwoven. You recall that astronauts aboard the International Space Station experience slightly slower aging due to their speed by mere milliseconds. Technically, space travelers are a tiny bit younger than their Earthbound counterparts. It's not enough to grant eternal youth, but it's enough to remind us that time is never entirely fair or equal. You float higher, realizing that your entire lifespan is delicately shaped by gravity's warping of time. Your moments, your days, your years, they are all measured out on clocks that tick in tune with the local curves of spacetime. It's oddly comforting, knowing that your existence is so intertwined with cosmic rules. You're not just drifting through life, you're riding the gentle warps and bends of time itself. Einstein's absent-minded grin comes to mind. Perhaps he knew that worrying about time's pace is futile, whether it stretches or contracts. It's all part of the same cosmic dance. So tonight, as you check your watch, remember, every tick is a tiny negotiation with gravity and motion. Time is elastic, and your lifespan, even if measured in the same familiar calendar years, is uniquely yours, flowing through curved spacetime in a quiet, personal rhythm. And next time someone complains that the week is dragging, just say, technically, your local curvature of spacetime might be to blame. It won't help Monday arrive faster, but it might make you sound impressively cosmic. Section 9. You're drifting gently back from your imaginary airplane seat, your cosmic tomato juice safely stowed, when the universe opens up around you into a vast ocean of darkness and starlight. And suddenly, you feel a subtle tension, as though the fabric of reality has edges you've never quite noticed before. Because tonight, you're going to peek toward cosmic horizons, boundaries drawn not just in space, but in time itself, where gravity might hide whole regions of the universe from your view. Imagine yourself floating far from any galaxy, lost in the intergalactic void. The stars fade into a faint mist behind you. Ahead, an invisible wall looms, a horizon beyond which you simply cannot see, no matter how powerful your telescope might be. Mainstream fact: in physics, horizons are boundaries created by gravity and the expansion of spacetime. The most famous example is the event horizon of a black hole, point of no return, where time slows to a crawl and light cannot escape. But our entire universe has its own cosmic horizon. Due to cosmic expansion, there are regions of space receding from us faster than light. Light from those regions will never reach us, meaning their stories are forever hidden beyond our cosmic horizon. Quirky Einstein tidbit: Einstein once wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. Physicists still argue whether he truly meant that time is an illusion, or whether he was speaking poetically about how spacetime blends everything together. Either way, you can almost hear his voice whispering through the darkness. Reality might be far stranger than it seems. Hovering there, you glance toward a distant galaxy, its light left over 13 billion years ago, traveling across a universe that has been stretching and expanding the entire time. But some galaxies have already slipped beyond the cosmic horizon. Their light, even if it departed this very moment, will never reach us. Physicists still argue whether there might be entire regions of the universe beyond our cosmic horizon, filled with different physical laws, different particles, perhaps even wildly different versions of reality. Are we living in a single cosmic bubble or one of countless bubbles in an ever-expanding multiverse? It's a question that hangs suspended between physics and philosophy, daring us to dream. Einstein's violin echoes again in your thoughts. You picture him drawing a slow, mournful note, fading into silence. Horizons are like that notia boundary past which sound, sight, and knowledge can't travel. Whether it's the edge of a black hole or the cosmic horizon, at the edge of the observable universe, these boundaries are time's hidden walls. Close your eyes and imagine drifting closer to a black hole's event horizon. From the outside, an observer would see you moving slower and slower, your image frozen in time. For you, time would flow normally, but the outside universe would appear to rush forward in fast motion. It's the ultimate one-way mirror, dividing space and time into separate realms. Physicists still argue whether information might somehow escape from inside black holes. Stephen Hawking once proposed that black holes slowly radiate energy, a process now known as Hawking radiation. But does that radiation carry the secrets of what fell in? Or is information lost forever behind the horizon's veil? The question remains one of the thorniest paradoxes in modern physics. Back at the scale of the cosmos, you turn your gaze toward the cosmic microwave background, faint glow left over from the Big Bang. It's our oldest light, painting the inside of our observable bubble. But beyond that glow lies a universe forever hidden from us. It's like living inside a room whose walls we cannot penetrate, no matter how loudly we shout. The quiet beauty of horizons is both comforting and unsettling. They remind us there are limits to what we can know, but also that there's always more beyond the veil, waiting to be discovered. Einstein would probably smile his quiet, mischievous smile and say horizons are nature's way of keeping things interesting. They preserve mystery, leaving just enough unknown for the next generation of curious minds. You float there, sensing the cosmic horizon expanding every moment as the universe stretches. The galaxies you see today might slip beyond your reach tomorrow, leaving you with a bittersweet sense of cosmic farewell. So tonight, as you gaze into the stars, remember, there are edges to what you can know. Gravity doesn't just warp space, and time might draw us invisible curtains across the cosmos. And next time someone tells you the sky's the limit, just lean closer and say, technically, there's a cosmic horizon. But don't worry, it's moving away faster than light. That'll either spark an incredible conversation or ensure you get the entire couch to yourself. Section 10. You're floating near that cosmic horizon, the echo of hidden galaxies humming at the edge of spacetime. When the universe gifts you a softer, more familiar tune, it's a melody threading through the stars, a gentle reminder that physics, like life, sometimes sings in harmonies. Because tonight, we're going to weave Einstein's love for music into how physicists imagine gravity orchestrating the rhythm of time itself. Picture yourself back in Einstein's cozy study. The lamp glows warmly, casting shadows over scattered equations and coffee rings. And there, leaning in the corner, is his violin. Its polished wood gleams, as though waiting patiently for fingers to dance across its strings. Mainstream fact: music was Einstein's great passion. He said, "Life without playing music is inconceivable for me." He often claimed that many of his insights in physics arrived while he was lost in musical thought. For him, melodies weren't just entertainment, they were a way of perceiving patterns, of feeling the logic hidden behind the universe's veil. Quirky Einstein tidbit: despite his love for music, Einstein wasn't universally adored as a performer. One critic who heard him play reportedly quipped that Einstein's violin skills violated the laws of harmony more than those of relativity. Physicists still argue whether Einstein's musical efforts were brilliant creative fuel or simply delightful chaos that provided comic relief for his friends. Either way, you have to admire a man who could revolutionize physics and still try to master a G minor concerto. Floating in that study, you watch Einstein lift the violin to his chin. As the bow glides across the strings, a pure note sings into the air. Vibrations ripple through the wood and into the room, echoing off bookshelves and chalkboards. And suddenly, you see the connection. Music and gravity are both about vibrations and curves. Sound waves ripple through air, Gravitational waves ripple through spacetime itself, stretching and squeezing reality as they pass. Physicists still argue whether these cosmic sounds could one day reveal hidden truths about the universe. Could gravitational waves carry faint signatures from exotic physics like clues to new dimensions, or whispers from cosmic strings? Or will they remain the low, gentle murmurings of black holes and neutron stars colliding? The debate hums on, like unresolved chords in a symphony waiting for resolution. Imagine the universe as a grand orchestra. Each massive object a star, a planet. A black hole plays its own instrument, plucking at the cosmic fabric and sending vibrations outward. Spacetime isn't a silent void. It's a resonant medium through which gravity sings. Einstein's violin flickers into your mind again. The tightness of each string determines its pitch. Stretch it tighter, and the note grows higher. In a similar way, the curvature of spacetime changes how time flows. Stronger gravity stretches time, slowing it down, lowering the tempo of moments. Weaker gravity lets time flow faster, like quick notes dancing across a violin's fingerboard. You hover above Earth once more, sensing how the planet's mass sculpts a gentle curvature in spacetime. It's as though Earth is plucking a deep, soft bass note into the cosmic score. And your seconds, your minutes, your entire life unfolds along that rhythm. Physicists still argue whether the universe itself might be built from vibrations. At the most fundamental level, string theory proposes that everything particles, forces, even spacetime is made of tiny, vibrating strings whose frequencies determine what they become. A quark, a photon, a gravitonal are different notes in the universe's hidden symphony. Einstein might never have known about string theory, but you suspect he'd have adored the idea. To him, music and physics were twins, both revealing invisible patterns hidden beneath appearances. Floating in the glow of starlight, you imagine gravitational waves washing over you, subtly stretching and compressing the fabric of your existence. Detectors like LIGO listen for these faint cosmic murmurs the way human ears strain for the softest notes of a violin. Each wave is a story and narrative written in spacetime's undulating curves. Einstein, bow in hand, might have understood that time itself is a rhythm, sculpted by gravity's silent score. When gravity changes, the tempo of time changes. Seconds slow down, stretching like a drawn-out musical phrase. So tonight, as you lie beneath your blankets, let your breath fall into rhythm, slow and measured. Feel the quiet tempo of the universe, where even your heartbeats trace curves in the cosmic fabric. And if anyone ever teases you for humming softly to yourself, just tell them you're tuning into gravity's hidden song. It might not get you a record deal, but it'll definitely keep you in harmony with the universe. Section 11. You're floating there, the last trembling note of Einstein's violin fading into silence. When the universe seems to inhale around you, the stars blink slowly, darkness presses close, and you sense an even bigger question rising like a tide. Because tonight, you're going to consider how gravity's grip on time might shape not only the fate of galaxies and black holes, but the ultimate destiny of the universe itself, and us along with it. You drift higher, out past clusters of galaxies, past clouds of hydrogen gas glowing in cosmic filaments. The farther you go, the clearer it becomes. Gravity's reach is not merely local. It threads the entire cosmos together like invisible silk, sculpting not just where things are but when they happen. Mainstream fact: for decades, astronomers assumed that gravity would eventually slow the universe's expansion. Maybe it would even reverse it, leading to a big crunch. But in the late 1990s, scientists discovered something astonishing. The expansion is speeding up. Some mysterious force dubbed dark energy is pushing galaxies apart faster and faster. Gravity, for all its cosmic power, seems to be losing the ultimate tug-of-war. Quirky Einstein tidbit: Einstein once introduced a cosmological constant into his equations, trying to keep the universe static because he thought an expanding cosmos seemed absurd. When Hubble showed the universe was expanding, Einstein called that constant his biggest blunder. Physicists still argue whether it was truly a mistake or a brilliant premonition of dark energy. Either way, it's one of science's finest cosmic face bombs. Hovering above galaxies, you ponder what happens to time if the cosmos keeps expanding forever. If space stretches infinitely, then time might stretch too. Distant galaxies will fade from view, sliding over the cosmic horizon, leaving us adrift in an ever lonelier void. Physicists still argue whether dark energy is a true constant force, or whether it might change over time. Could it strengthen, ripping apart galaxies, stars, even atoms in a catastrophic Big Rip? Or might it fade, letting gravity regain control? The universe's ultimate fate is still an open-ended mystery, written in equations whose meaning we haven't fully deciphered. Einstein's violin echoes faintly in your mind. You imagine him bowing a note that rises steadily in pitch, a musical metaphor for the accelerating expansion of spacetime. A universe speeding up is like a tempo increasing in a cosmic composition, drawing the final movement toward some unknown crescendo. You drift past ancient galaxies glowing faintly in infrared, their light stretched by billions of years of cosmic expansion. Each photon you catch is older than human civilization itself, and you realize time and space are inseparably linked. If space expands, time unfurls alongside it. The rhythm of reality itself changes. Physicists still argue whether gravity could someday halt this runaway expansion. Could some hidden feature of spacetime reverse the tide? Might exotic particles or quantum effects intervene, binding the cosmos back together for a final cosmic encore? Or is this lonely future inevitable, with each galaxy fading into its own island universe? It's the sort of question that might keep you awake at night unless, of course, you remind yourself that the timescales involved are so vast, they make human worries look like flickering fireflies. We're talking tens or hundreds of billions of years. Plenty of time to finish your Netflix queue first. Hovering there, you realize gravity's role isn't merely to shape orbits or warp seconds. It's the universe's hidden scriptwriter, shaping the entire cosmic plot. If dark energy remains dominant, the cosmos might thin out into a dark, silent plane where stars stop forming and black holes slowly evaporate, leaking Hawking radiation into endless night. But even then, gravity leaves its mark. Black holes persist longer than stars. Clusters of matter cling together in pockets of resistance. Time flows ever onward, tracing the legacy of gravity's unseen fingers. Einstein would have found it beautiful and terrifying all at once. The notion that time itself might eventually lose meaning if the stars vanish into darkness. You drift back closer to Earth, feeling the gentle tug of its gravity on your imaginary cosmic self. And you understand that even if the universe's fate seems remote, the same force that might shape cosmic destiny also shapes your life moment by moment. Every heartbeat, every memory, every whispered word is measured out on gravity's invisible clock. So tonight, as you close your eyes, remember, the universe's fate is not just written in distant galaxies. It's also written in the seconds ticking softly beside your bed. Gravity is the thread tying your life to cosmic history and possibly to cosmic destiny. And next time someone frets about the future, just lean in and say, relax, the heat death of the universe is at least a trillion years away. It may not solve their immediate problems, but it's excellent perspective. Section 12. You're floating back toward Earth now, trailing stardust and cosmic questions. Your mind swirling with visions of black holes, stretching seconds, and the distant hush of the universe's fate. And finally, you begin to sense something deeply personal rising through the cosmic static. Because tonight, we come full circle to your own life, and how your personal story unfolds upon gravity's curved stage. You find yourself drifting gently above Earth, watching the planet spin beneath you. Clouds swirl over oceans, city lights glitter like sapses in a colossal brain, and mountains cast long shadows across dawn-lit plains. And you feel a quiet truth settle in your chest. Your existence is not separate from this cosmic dance. Mainstream fact: every single atom in your body was forged in stars. The calcium in your bones, the iron in your blood, the oxygen in your breath all birthed in nuclear furnaces billions of years ago, scattered through supernovae, and gathered into the shape that is uniquely, wonderfully you. Quirky Einstein tidbit: Einstein once said that he never cared much for the idea of free will. He believed our choices were shaped by forces beyond our control, including the geometry of spacetime itself. Physicists still argue whether free will can exist in a universe where time is woven into a four-dimensional block where past, present, and future might all coexist. Either way, Einstein would probably have reassured you that even if your choices are determined, they're still beautifully, cosmically yours. Hovering above the planet, you feel the weight of gravity tugging at you, a gentle reminder that you're bound to Earth's surface by the same force that shapes galaxies, curves time, and sculpts black holes. Gravity is intimate. It's not merely cosmic drama. It's the reason your feet find the ground every morning, and why your coffee stays politely in the cup instead of levitating away. Physicists still argue whether gravity might be an emergent phenomenon arising from deeper principles, like quantum information or entropic forces. Could gravity be the visible ripple of invisible patterns, or is it fundamental, a primal force built into the universe's core? The debate waltzes on, bridging physics and philosophy, leaving us perched on the edge of wonder. You drift lower, closer to rooftops and trees. You see people going about their lives long, arguing, hugging, staring into phones, dreaming dreams both big and small. None of them might be thinking, in this moment, about how gravity shapes their days. Yet it does. Every tick of the clock beside your bed, every moment your heart beats, every second you love someone or feel sorrow or wonder, all of it is measured out along the curved contours of spacetime. Einstein's violin glimmers in your mind again. You imagine him standing by a window, bow gently caressing the strings, coaxing a soft, delicate tune. Perhaps, in those quiet hours, he felt how music and life and physics are not so different. All follow rhythms, shaped by forces both seen and unseen. You begin to understand, your life is a unique curve through spacetime. Physicists call it a world line, a path traced by your existence, from birth to every choice, every breath. Your world line winds and weaves through the geometry of the universe, a singular thread woven into the cosmic tapestry. So you, too, are part of gravity's story, not just in the sense that you fall down or feel heavy on your feet, but because your moments, your seconds, your entire life unfolds along gravity's hidden slopes. Time flows differently depending on where you stand, how fast you move, and how massive the world around you is. Physicists still argue whether consciousness itself might be influenced by spacetime's geometry. Could the shape of your personal time define the shape of your thoughts? Or is the mind its own quiet cosmos, obeying rules we've only begun to glimpse? The question lies at the frontier where physics blurs into philosophy, a place Einstein himself often wandered. Hovering there, you realize something beautiful. Gravity doesn't just bind planets and stars. It gives shape to your days. It defines the rhythm of your hours. It ties your story to the stars. So tonight, as you lie under your blanket, remember, you are woven into the fabric of spacetime. Gravity shapes your laughter, your dreams, your memories. Your seconds ripple outward, leaving gentle impressions on the cosmic cloth. And if the weight of life ever feels heavy, know that it's the same gentle force that binds galaxies together. You are part of the universe's quiet beauty, curving time and space with your very existence. And next time you feel insignificant under the stars, remind yourself, gravity's fabric cradles you. Your world line is unique, and you are an essential thread in the universe's vast, shimmering tapestry.